third lecture in Module 8 on numerical solution of Navier-Stokes equations. In this module, we have already discussed the basic features of Navier-Stokes equations. We discussed explicit and implicit time integration algorithms, and today we would focus on implicit pressure correction methods, and in the next lecture we will take up fractional step methods. Before we proceed further, let us have a recapitulation of what we discussed in the previous lecture. We briefly discussed the numerical simulation of compressible flows, and then we took up the algorithms for numerical simulation of incompressible flows. We had a look at explicit time integration methodology and implicit time integration methodology, wherein we saw that we have to solve a very large system of coupled nonlinear equations in case we use an implicit time integration technique. Implicit time integration techniques are required if you want to solve slow transient or steady state problems. So, is there a way out in which we can avoid solving a very large system of coupled nonlinear equations accurately? So, implicit pressure correction methods, which we discuss in this lecture, provide an answer wherein we would develop an iterative technique to solve the coupled nonlinear system of equations. So, we will first discuss very briefly the basic feature of what we call implicit pressure correction methods, and then we will take up few popular algorithms of this category, in particular simple, simplex and simpler. If time permits, we will also take up fractional step methods, or else we would take this topic up in the next lecture. Now, these implicit pressure correction methods, they are primarily used for steady and slow transient flows, and once again the basic process is very similar to what we discussed earlier in the case of explicit time integration techniques. That is to say, we would first find out a velocity field which does not satisfy the continuity equation, then we will solve a Poisson equation for pressure and incorporate a correction term which would enforce the continuity, thereby obtaining a velocity field which is divergence free. So, implicit pressure correction methods follow the same procedure, and they belong to the general class of methods which we call projection methods, wherein we first project a velocity to get an intermediate velocity field which does not satisfy continuity and correct it using a pressure like term. And we will employ an implicit time integration, unlike explicit time integration techniques, along with the pressure and or a pressure correction equation to enforce mass continuity. We will first discuss a scheme which bases the corrections on the pressure equation, and then we will take up simple algorithm which is based on the pressure correction, use a pressure correction to enforce the continuity equation, and simpler algorithm which would involve both pressure and pressure correction solution. Now, in the last lecture we had written, or we had obtained, the discrete momentum equation which we would obtain from spatial discretization. In fact, it was a semi-discrete equation in time, and when we applied an implicit time integration technique such as backward Euler, we got a system of nonlinear equation. Now, that nonlinear momentum equation, that can be written in a quasi-linear form as APVI VIP n plus 1 plus sigma L ALVI VI subscript comma L n plus 1 is equal to QV n plus 1 minus delta P n plus 1 by delta Xi P, but this del by del Xi, this represents the discretization for the pressure term. Now, here the P is the index of an arbitrary velocity node at a given computational nodes, L are the indices of its neighboring nodes which contribute to that momentum equation, and I could take values from 1 to 3 corresponding to 3 momentum equations. Now, remember here this Q terms and A's, they will depend on the unknown velocity field. One more thing, we have been using this comma notation we have used earlier for to denote differentiation, but not in this equation. Here I comma p, that only say that we are dealing with the ith component of velocity or ith momentum equation, and capital P subscript that denotes a particular computational node. Similar in I comma L, this comma again does not denote differentiation, it simply says that we are looking at the ith momentum equation for the neighboring node L. So, here comma does not denote differentiation. Now, the source term q and coefficients a that depend on unknown solution v n plus 1. So, if we can devise an iterative scheme, we have to work or we have to use the values which are known till now. Now, these discretized momentum equations, they represent a set of coupled nonlinear equations, because we will have 3 such equations for each value of I, and we have to solve these equations iteratively. And in case if you are looking for an accurate time history, what we will have to do is we have to continue the iteration at each time step for this nonlinear system to a specified tolerance. Now, in this context, what do we do? At each time step we have to solve our nonlinear system, and usually we are dealing with a very large system of linear equations or what we call linearized equations. So, we would use 2 sets of iterations. One is what we call outer iterations, and other set of iterations are referred to as inner iterations. So, let us clarify these terms. The outer iterations are the ones, the iterations at each time step in which our coefficients a and the source term q are updated based on the velocity field and the pressure field computed at the previous iterations. So, these iterations wherein these coefficients a and q are updated, they are called outer iterations. Now, what are inner iterations? Iterations for solution of linear systems with fixed coefficients a are called inner iterations. Now, these inner iterations were required, or they refer to the iterations required in the solution of our velocity field from linearized equations, or we would also use very often an iterative solution procedure to solve the pressure Poisson equation. So, these iterations which are required or which are involved in the solution of the linear algebraic equations for velocity field and the pressure field, these would be referred to as our inner iterations. Now, let us derive the algorithm before we look at the summary of this particular scheme. Okay, so let us rewrite our discretized momentum equation. Discretized and it is also quasi-linear form. So, we had this A P V I V I comma P n plus 1 plus sigma L A L V I comma L n plus 1 is equal to q V I n plus 1 minus delta P n plus 1 or delta x I, the computational node P. Let us call this equation as 1. So, we will have a set of 3 such coupled equations, and in this quasi-linear form we have taken one precaution, that is to say we would put all the terms on the left hand side for a particular velocity component, that is I equal to 1, rest of them they would be put together in this term QVI. So, this QVI n plus 1 contains all the terms which are evaluated using previous values which may be evaluated using values at previous time step that is our known values, that is Vi at n, any body force term and linearized velocity terms or linearized terms which may contain, in fact they would usually contain the 8 unknown velocity components. This region we have used the superscript n plus 1 to denote that is this given this q term, which is sort of our load term for a linearized system, that also depends on 8 unknown values. Now, to start of the iteration process, we want to devise an iterative solution scheme, and let us use symbol m to denote our outer iteration. So, let m denote the counter for outer iterations. So, what we will try to do is that at each iteration we will have to solve this linearized system using values which are already available, that is which have been evaluated at the current iteration, which are available to us. So, at each outer iteration we have to solve this linearized equation 1 using values of A, Q and P, okay, obtained at previous iteration. Or if we are at the very first iteration, we will say or at previous time step. So, at the start of the outer iterations, our known values are the values at time t is equal to T n. So, those would be used as our initial guess for the field values at the new time step, and we would solve for an intermediate velocity field, since on the right hand side we are using the terms which are based on the previous iteration, and if we substitute those in our equation, they will not satisfy the momentum equation 1, and the velocity field which we obtain thereby, that will not satisfy the continuity equation either. So, thus what do we do, that we would solve for, or thus we do not try to immediately obtain an estimate of the velocity field at the current iteration which would satisfy continuity. We would rather obtain a velocity field estimate which does not satisfy continuity, and we would enforce the continuity later on. So, thus we obtain an intermediate value for velocity field VIM. Let us denote it by VIM star which is the solution of AP VI comma P M star plus sigma L AL VI comma L M star. In equation 1 we have just substituted M star in place of superscript n plus 1 Q VI M minus 1 minus delta P M minus 1 over delta Xi at P. So, let us call this equation as 2. In fact, this represents not a single equation, it represents a system of equations which had to be solved, and if you can solve the linear system we can get our intermediate velocity field VI M star. And let us emphasize this point that intermediate velocity field VI M star will not satisfy the continuity. Okay, now what do we do to enforce the continuity? Let us rewrite this equation slightly, and that would give us an equation which we can use as our starting point to obtain a corrected velocity value which would satisfy the continuity equation. So, let us rewrite equation 2 . Let us keep only VI P M star on one side. So, VI comma P M star, this is equal to 1 over AP VI in brackets Q VI M minus 1 minus sigma L AL VI comma L M star minus 1 over APVI delta P M minus 1 over delta Xi at P. Let us call this equation as equation 3. This equation will not actually be used to compute anything, this is just an intermediate step in our derivation process. And let us introduce it and the modified velocity field. So, let us introduce velocity field defined as, we will call it VIP M star tilde. In fact, this is shorthand notation for the first term on the right hand side of equation 3. This is 1 over APVI QVI M minus 1 minus sigma L ALVI VI comma L M star. Let us call this definition algebra equation 4. So, in terms of this modified field, so thus our equation 3 can be rewritten as, let us go to the next. So, V I P M star is given by V I P M star tilde minus 1 over A P V I delta P over delta X I M minus 1 at point P. Now, it is not this equation per se which is very important. What is important in the development of algorithm is the form of this equation. Let us call this equation as 4a. Now, what this equation suggests is that if we had the pressure value at the current instant, that could be used in this equation, and if you could have used that, we should be able to obtain a corrected value for the velocity field, that is to say the velocity field at the current iteration. So, this form of equation 4a suggests that velocity field at current iteration can be obtained from V I comma P M. Now, we have dropped this star, it is no more the intermediate velocity. What we are claiming that this would be our continuity satisfying velocity field at the current outer iteration M. So, V I comma P M star tilde minus 1 over A P V I delta P over delta X I M. Now, here the pressure is no more the known pressure, in fact, this is an unknown pressure value at the current iteration which we have got to find out. Okay. The first term is known because we can obtain we can obtain V I M star from the solution of our linearized system. So, the first term is known. Now, let us enforce the continuity. So, this V I M must satisfy our continuity equation, that is delta V I M over delta X I is equal to 0. Remember, we are dealing with incompressible flows, hence let us take the divergence of equation 5. So, what do we get? The first term delta V I P M over delta X I delta over delta X I of V I M star at point P minus delta over delta xi of 1 over APVI delta Pm over delta xi. First term should be 0 because Vim satisfy the continuity equation. So, this leads to our discrete pressure Poisson equation delta over delta xi of 1 by APVI delta Pm over delta xi at computational node P should be equal to delta over delta xi Vi m star. So, this is our pressure Poisson equation. This is discrete Poisson equation for pressure Pm. Let us call this equation 7. So, now let us have a look at the summary of the equations which we have got. We had linearized momentum equation 2, which was for the intermediate velocity field Vi m star. So, we can solve that equation using values of the velocity at the previous iteration and the pressure at previous iteration. So, Vi m star is known. Next, we can solve for our discrete Poisson equation for Pm, and now this Pm can be used in conjunction with Vi m star to obtain the velocity field at the current iteration, which would satisfy our continuity equation. Okay. So, now let us summarize these steps and put this algorithm in formal terms. So, let us using velocity and pressure at previous iteration level, that is Vi m minus 1 and Pm minus 1, or at previous time step for m is equal to 1, solve the linearized momentum equations to obtain Vi m star, and once this Vi m star is known, okay, now we will compute the modified velocity field Vi m star tilde, find out its derivatives, because that is what would be used in our pressure Poisson equation. Okay. And once that is known, then we can compute the corrected velocity field Vim, which would satisfy the continuity equation. Next step would be to check if our velocity field Vim and pressure field Pm, they satisfy momentum equation to the specified tolerance. If the answer is yes, then we will say this Vim and Pm now represent the values at the current time step, and we will proceed for the computation at next time step. If not, we will reset this iteration counter as m is equal to m plus 1 and then go back to step 1. So, this is in nutshell our implicit pressure correction method based on an implicit time integration scheme and a linearization procedure. Now, there are many variants of this implicit pressure correction method which have been proposed in the CFD literature. There are some variants which suggest that we can use the values at the previous iteration level, and we just need to add a small correction to get the corrected velocity values. That is to say that velocity field computed from linearized momentum equation and pressure Pm minus 1 can be taken as provisional values to which small corrections must be added to obtain the final values for the current outer iteration. That is, Vim could be obtained as Vim star plus a small correction Vi prime, and similarly Pm is equal to Pm minus 1 plus a small correction P prime. We will have a look at one such method which is called simple. This was the first algorithm. Its name was given as simple by Pattankar and Spalding in 1972, and simple essentially is an acronym. It is semi-implicit method for pressure linked equations. So, each first letter of each of these words that is involved in this word simple. Okay. And there are various improvements of simple such as simpler, simplec and piso. They have been put forth in literature. For the details, please see the books by Fersiger and Parikh and Versteeg and Malala-Sekera. In this lecture we have got time only to discuss simple, and in next lecture we will take up simplec and simpler schemes. So, now let us have a look at the equations which are involved in the simple algorithm. So, let us get back to our board. This algorithm is based on what we have discussed earlier for our implicit pressure correction method. So, many of the equations which I have derived, they would be used as such. The crux is that we want to represent our corrected velocity V I m as V I m star plus a small correction added V I prime, and similarly for pressure that P m is obtained by P m minus 1 plus small correction P prime. So, let us continue the same numbering scheme. Let us call this equation as 8. Now, if we substitute these equations, so substitution of 8 in linearized momentum equation which we have obtained for V I m star gives the following a relation between velocity and pressure corrections. So, this relationship is V I P prime, this is equal to V I comma P tilde prime minus 1 over A P V I delta P prime over delta x I point P. This has got a form very similar to the relation which we have written for V I m star. So, here again this V I P prime tilde, this is equal to minus 1 by A P sigma L A L V I V I L prime. Okay, let us call this as 10. Now, what would be our, if you substitute 9 in 8, our corrected velocity field is given by V I m is equal to V I m star plus V I P tilde minus 1 over A P V I delta P prime over delta x I at P. Now, this must satisfy our continuity equation. So, satisfaction of continuity equation requires delta V I m over delta x I is equal to 0, and this leads to delta over delta x I of V I m star plus delta V I p prime tilde over delta x I p minus delta over delta x I 1 over a p v I delta p prime over delta x I at p. So, if you look carefully, this equation is a discrete Poisson equation for the pressure correction P prime. The first term on the left hand side, that is known, that is because V I m star, that would have been obtained from the solution of linearized momentum equation, but as V I p tilde prime, that is unknown. We still do not know what our velocity corrections are. So, what do we do then? One of the options which Pattankar suggested was this V I p tilde prime is unknown. So, as the first approximation, so let us ignore it. So, if you ignore it, then what happens? Then equation 11 becomes delta over delta x I of 1 over a p v I delta p prime over delta x I at p is equal to delta V I m star delta x I at p. So, this is Poisson equation for pressure correction, and similarly if we have just simply set V I tilde to 0. So, equation 9 becomes, or velocity correction equation becomes, that V I p prime is minus 1 over a p v I delta p prime over delta x I p. So, let us call this equation as 13. So, now we have got an algorithm wherein what we need to do is, first let us obtain the intermediate velocity field V I m prime, use that to obtain a pressure Poisson equation, solve this pressure Poisson equation to get P prime. Once we have this pressure correction field, we get the velocity corrections added to the velocity value, we get the velocity field added to the previous pressure value, we will get updated pressure value. So, now here we have got one problem here. Let us note down that the central approximation which we have made, or the main approximation, of simple algorithm, that is we have set this V I prime tilde to 0. Okay. Now, let us have a look, let us formalize the steps in an algorithm form. So, the first step is very similar to what we have seen earlier, that is use velocity and pressure at previous iteration level or at previous time step to solve for V I m prime, compute its derivatives and solve the Poisson equation for pressure correction P prime, then compute the velocity correction Vi prime, updated velocity field Vim and pressure Pm, then check for the convergence whether the fields Vim and pressure field Pm satisfy momentum equation. If yes, terminate the iterations for the current time level, go to next time level, or else increment the iteration counter and go to step 1 and repeat the simple algorithm iterations. Now, we have ignored one term which was not known, and that leads to a slow convergence of simple iterations. So, what Pattankar noted is to improve the convergence, we must use under relaxation for pressure and velocity corrections. We will not add the total value of P prime and V prime which we calculate, we would instead weight them by small factor and that factor would be less than 1. So, Pm would be given as Pm minus 1 plus alpha P times P prime, where alpha P is a value less than 1. Similarly, Vim is Vim star plus alpha V Vi prime. So, in theory we can have different under relaxation factors alpha V for each of the velocity components, but normally we take the same values. The values which were recommended by Pattankar, they are 0.8 and 0.5, 0.8 for the pressure correction and 0.5 for the velocity correction. It and the recommendation is let us choose our velocity correction or velocity under relaxation factor alpha V, and alpha P is chosen to be 1 minus alpha V. So, there are two recommended set of values which help in improving the convergence of simple algorithm. For further details, you can look at these books by Anderson, Chung, Fertziger and Versteegen and Malala-Sekera. So, in this lecture we will stop here. In the next lecture we will have a look at the improved version of simple algorithm, and we will also take up fractional step methods.